Good evening. Tonight, you'll discover the secrets of one of nature's most enchanting phenomena, the aurora borealis, the northern lights. You'll learn how curtains of green and purple light dance across polar skies, how ancient peoples interpreted these celestial displays, and how modern science explains the magic above us. 100 facts about the northern lights that will guide you into the most peaceful sleep. But first, if you want more journeys like this, subscribe to the channel and leave a like right now, because in just a few minutes, you'll be too relaxed to move. Now then, make yourself comfortable. Let your body sink into your bed. Close your eyes. Tonight, I invite you on a journey to the far north, to places where night skies come alive with color, where ancient peoples watched in wonder, where science and beauty meet in perfect harmony. 100 remarkable facts, told slowly, gently, without haste. You don't need to remember them. You don't need to analyze them. Just listen and let these words become part of your dreams. Breathe evenly, deeply, and we begin. The northern lights, or aurora borealis, are one of Earth's most spectacular natural light displays. They appear as shimmering curtains of light, dancing ribbons, glowing arcs that stretch across the night sky. Colors shift and change: green, purple, red, blue, pink, sometimes all at once, sometimes fading from one to another like a slow watercolor painting. Imagine standing beneath them, the cold Arctic air on your face, and above you, the sky itself seems alive, moving, breathing, dancing. The name aurora borealis comes from two sources. Aurora was the Roman goddess of dawn. She would race across the sky each morning, announcing the arrival of the sun. Borealis comes from the Greek word for north wind, boreas, together. Aurora borealis means the northern dawn, a beautiful name for a beautiful phenomenon. The scientist Galileo Galilei is believed to have coined this term in 1619, though he never saw the lights himself from his home in Italy. The northern lights occur in an oval shape around the North Pole. This region is called the auroral oval. It's a band that circles the magnetic North Pole at a distance of about 15 to 20 degrees latitude. Within this oval, the lights are most frequent, most vibrant, most likely to appear on any given night. The auroral oval isn't fixed. It expands and contracts, growing larger during periods of high solar activity, shrinking during quiet times. If you're still awake, imagine that oval, a ring of light around the top of the world, constantly shifting, constantly changing. The northern lights occur at altitudes between 60 and 600 miles above Earth's surface. That's much higher than where airplanes fly, higher than weather patterns, higher than the clouds. Most auroras occur between 60 and 120 miles up, in a region of the atmosphere called the thermosphere. At these heights, the air is incredibly thin, so thin you couldn't breathe it, yet is dense enough to glow when struck by particles from space. The southern hemisphere has its own version of the aurora. It's called the aurora australis, the southern lights. They occur in a ring around the South Pole, just like their northern counterpart, with the same colors, the same movements, the same ethereal beauty. The physics is identical. The only difference is geography. Few people see the southern lights because most of the auroral oval lies over Antarctica, a frozen continent with no permanent human population. But they're there, dancing in solitude, unseen by human eyes most of the time. Interesting, isn't it? The northern lights are caused by the sun, Our star constantly releases a stream of charged particles, electrons and protons, flowing outward in all directions. This stream is called the solar wind, and it travels through space at incredible speeds, about 250 miles per second. When this solar wind reaches Earth, something magical happens. Earth has a protective magnetic field. This field extends thousands of miles into space, creating an invisible shield around our planet. The magnetic field deflects most of the solar wind, keeping us safe from radiation, allowing life to flourish. But at the poles, the magnetic field lines converge. They funnel inward, creating pathways. And along these pathways, some solar particles can enter Earth's atmosphere. When solar particles collide with gases in Earth's atmosphere, light is produced. Think of it like a cosmic neon sign. In a neon tube, electricity excites gas atoms. They emit light. In the aurora, solar particles excite oxygen and nitrogen molecules, and they too emit light. Different gases produce different colors. The composition of the atmosphere at different altitudes creates the palette we see. Green is the most common aurora color, that beautiful pale green, like spring leaves illuminated from within. It comes from oxygen molecules about 60 to 150 miles above the surface. When oxygen atoms are struck by solar particles at this altitude, they emit green light. This is the color most often photographed, most often seen. The signature hue of the northern lights. If you've seen pictures of the aurora, chances are they showed cascading curtains of green. Red auroras come from oxygen at higher altitudes. At heights above 150 miles, oxygen atoms emit red light when excited. These red auroras are rarer. They require more energy, and they often appear at the top edges of green auroras, like a crimson crown, in intense displays. The entire sky can glow red. Ancient peoples sometimes mistook these displays for fire in the sky. Let your breathing slow. We have so much more to discover. Purple and violet hues come from nitrogen. When solar particles strike nitrogen molecules, they can produce purple, violet, or blue light. These colors usually appear at the lower edges of aurora displays, sometimes as a subtle fringe, sometimes as bold streaks. Purple auroras often have a delicate quality, like silk scarves draped across the heavens. Blue auroras also come from nitrogen, but they're quite rare. They appear at the very lowest altitudes where auroras can form. Below 60 miles, the blue is often intense, electric, almost shocking against the darkness. But most people never see a purely blue aurora. They're uncommon, special, a gift when they do appear. The intensity of the northern lights depends on solar activity. Our sun goes through cycles, periods of high activity, followed by periods of calm. During solar maximum, when the sun is most active, auroras are frequent and intense. They can be seen at lower latitudes. They light up the sky with brilliant colors. During solar minimum, auroras are quieter, less frequent, confined more closely to the poles. The sun follows an 11-year cycle, 11 years from one solar maximum to the next, then 11 more years. Scientists track this cycle by counting sunspots, dark patches on the sun's surface that indicate magnetic activity. More sunspots mean more solar activity, more solar wind, more auroras. The last solar maximum occurred around 2014. The next is expected around 2025. If you're still listening, you might witness particularly spectacular auroras in the coming years. Solar flares can create especially brilliant auroras. A solar flare is a sudden explosion of energy on the sun's surface. It releases massive amounts of radiation and charged particles. When these particles reach Earth, usually 1 to 3 days later, they can trigger intense geomagnetic storms. During these storms, the auroral oval expands. The lights become brighter, more colorful, more active. They can be seen much farther from the poles than usual. Imagine that. The sun sneezes, and days later, skies light up halfway around the world. The best places to see the northern lights are near the Arctic Circle. This includes northern parts of Norway, Sweden, Finland, Iceland, Alaska, Canada, Greenland, and Russia. Cities like Tromsø in Norway, Fairbanks in Alaska, and Yellowknife in Canada are famous aurora viewing destinations. These locations sit directly beneath the auroral oval, offering front row seats to nature's greatest light show. Darkness is essential for viewing auroras. This seems obvious, but it's worth stating. The lights are there during the day too, but sunlight drowns them out. You need dark skies, preferably far from city lights, away from light pollution. The darker your surroundings, the more detail you'll see, the subtler colors, the delicate movements. Winter offers the best viewing conditions in the Arctic, from September through March. The nights are long in the far north. Sometimes the sun barely rises at all. This extended darkness provides many hours each night for potential aurora viewing. The cold, clear winter air also helps. Less moisture, less atmospheric interference, crisper views. Bundle up warm, and the winter sky might reward you with unforgettable beauty. But auroras occur year-round. They don't stop during summer. The physics doesn't change with the seasons. It's just that summer brings midnight sun to the Arctic. 24-hour daylight, no darkness in which to see the lights. The auroras are still there, dancing invisibly above, waiting for autumn to reveal them again. The lights are most active around midnight, specifically between 10 p.m. and 2 a.m. local time. This is when the aurora is typically brightest and most dynamic. Scientists call this the magnetic midnight, when Earth's magnetic field is optimally aligned for particle entry. So if you're aurora hunting, plan to stay up late or wake up in the middle of the night. The best shows often happen when most people are asleep. Interesting, isn't it? You can sometimes see northern lights from surprising locations. During major geomagnetic storms, the auroral oval expands significantly southward. People in Scotland, northern England, northern Germany, and even sometimes in the northern United States have seen auroras. There are historical records of auroras being seen as far south as the Mediterranean, the Caribbean, even the tropics during extreme events. The famous aurora of 1859, which we'll discuss later, was seen near the equator. The northern lights make sounds, but rarely. For centuries, people reported hearing crackling noises, whooshing sounds, whispers. Scientists were skeptical. Sound doesn't travel well through the thin upper atmosphere where auroras occur. But recent research suggests that sometimes, during very intense displays, electromagnetic energy can create acoustic phenomena much closer to the ground. Faint crackles and pops, barely audible, like the sky itself is speaking. Most people never hear aurora sounds, but a lucky few, in the right conditions, have reported them. Photography has changed how we perceive the northern lights. Modern cameras, with long exposures, can capture colors and details invisible to the naked eye. Many photos show vibrant pinks, purples, and reds that a human observer might barely detect. This isn't false advertising. The colors are really there. Cameras just gather light more efficiently than our eyes. So if you see the northern lights in person, and they seem less colorful than photos, don't be disappointed. You're seeing them as they truly appear to human vision, which has its own subtle magic. The KP index measures auroral activity. It's a scale from 0 to 9. 0 means quiet. 9 means extreme storm conditions. At KP 0 or 1, auroras are dim and confined to the far north. At KP 5 or 6, they're visible across much of Alaska and northern Canada. At KP 7 or higher, they can be seen from northern tier US states and southern Canada. Aurora enthusiasts check the KP index the way others check weather forecasts. Modern technology helps predict auroras. Satellites monitor the sun constantly. They can detect solar flares and coronal mass ejections, then calculate when those particles will reach Earth. This gives us advance warning, usually 1 to 3 days. Websites and apps provide aurora forecasts. They tell you when conditions are favorable, when to look up. It's not perfect prediction, but it's remarkably helpful. Let your mind drift now. We've only begun our journey. Ancient peoples around the world created stories to explain the northern lights. Without modern science, they interpreted the lights through their cultures, their beliefs, their imaginations. These stories are beautiful, diverse, rich with meaning. They remind us that humans have always looked at the sky with wonder. Norse mythology associated auroras with the Valkyries. The Valkyries were warrior maidens who served Odin. After battles, they would ride across the sky, choosing which fallen warriors would be taken to Valhalla. Some believed the northern lights were the reflections of the Valkyries' armor and shields, glinting, shimmering, as they rode through the heavens. The lights became a sign of these divine choosers, moving between worlds. Some Norse peoples believed the lights were a pathway, a bridge between the earthly realm and the realm of the gods. The Bifrost, though more commonly associated with rainbows, the shifting colors, the undulating movement, it seemed like a road through the sky, a road that souls might travel, or that gods might descend. The Sami people of northern Scandinavia held complex beliefs about the aurora. The Sami have lived in the Arctic for thousands of years. They knew the lights intimately. Some Sami groups believed the lights were the souls of the dead, dancing, celebrating. But one should be respectful. Children were told to be quiet when the lights appeared, to stay indoors, to show respect. Making noise, waving, whistling at the lights was considered dangerous. It might attract the spirit's attention. Finnish mythology offers a particularly poetic explanation. The Finnish name for northern lights is revontule, foxfires. According to legend, a magical fox ran across the snow in the far north. Its tail swept the snow into the sky, creating sparks. These sparks became the northern lights, fire from fox fur, a creature of the wilderness, creating celestial beauty. The imagery is enchanting. A fox, glowing tail streaming behind it, painting the heavens. If you're still awake, picture that fox, running free beneath starlight. Indigenous peoples of North America developed diverse aurora traditions. Each group, each nation, had its own interpretation, shaped by their landscape, their experiences, their spiritual understanding. Some saw the lights as spirits, others as omens, still others as playful forces of nature. Some Inuit groups believed the auroras were spirits playing games, specifically playing ball with a walrus skull. The lights were the spirits running back and forth, kicking the skull across the sky. In some versions, the spirits were deceased relatives, still engaging in the activities they loved in life. The aurora's movement, its back and forth sweeping, resembled a ball game from this perspective. Other Inuit traditions said the lights were torches, torches held by spirits to guide the souls of the recently departed, helping them find their way to the land of the dead, a comforting belief that even in death there were guides, light in the darkness, the aurora as divine assistance, illuminating the final journey. Some Algonquin peoples believed the lights were the fires of their creator, the creator demonstrating his continued care for his people, showing he was there, watching over them. The northern sky would glow with these sacred fires, a reminder of connection between earth and the divine. Cree legends sometimes portrayed the aurora as messages from spirits trying to communicate with the living. The dancing lights were attempts at contact. Shamans might interpret these messages, reading meaning in the colors, the patterns, the intensity. The aurora became a form of language, a cosmic telegraph. Breathe slowly, deeply. Let these stories wash over you. In Estonia, the northern lights were believed to be the glow from a celestial wedding, a magnificent celebration happening somewhere beyond the visible world. The lights were reflections of that joyous event. It's a lovely interpretation, associating the aurora with happiness, with union, with celebration. Whenever the lights appeared, there was a wedding in heaven. Medieval Europeans sometimes feared the aurora. In latitudes where northern lights rarely appeared, their sudden visibility was ominous, unexplained. Red auroras especially were interpreted as blood in the sky, omens of war, plague, catastrophe. Historical records showed that significant aurora displays were sometimes followed by or coincided with periods of unrest. But this was correlation, not causation. The lights themselves were harmless, but fear gave them power. The Great Red Aurora of 1859 terrified many people. It appeared during the day, so bright it could be seen even in sunlight in some locations. People thought the sky was on fire, that the end of days had arrived. We'll talk more about this event later, but it's worth noting here as an example of how powerfully auroras could affect human emotions. In Japan, extremely rare aurora sightings were recorded with awe. So far from the poles, northern lights almost never appear over Japan, but historical records show occasional sightings during extreme solar events. These were viewed as divine portents, messages from the kami, the spirits. Artists attempted to capture them in paintings. Writers described them in poetry. Rare, sacred moments. Chinese historical records mention night rainbows, dating back thousands of years, accounts of colorful lights in the northern sky. Ancient Chinese astronomers were meticulous record keepers. They documented unusual celestial phenomena. Their descriptions of fire in the north and colored clouds at night almost certainly referred to aurora sightings during major geomagnetic storms. These records now help modern scientists study historical solar activity. Interesting, isn't it? Understanding the northern lights took centuries of scientific inquiry. From early observations, to theories, to experiments, to modern understanding. The journey mirrors humanity's broader quest to understand nature, to find explanations beyond mythology. The Greek philosopher Aristotle wrote about unusual lights in the sky. Around 330 BCE, he described what might have been auroras visible from Greece during a particularly strong solar event. He thought they were vapors in the upper atmosphere. catching light from the sun. Not correct, but it was an attempt at natural explanation rather than supernatural. In 1621, a French scientist named Pierre Gassendi coined a term for the southern lights. Though the northern lights were already called aurora borealis, there was no formal name for the southern version. Gassendi proposed aurora australis, southern dawn. The naming convention held, and now we use both terms. In 1741, Swedish scientist Anders Celsius began systematic aurora observations. Celsius, of temperature scale fame, was fascinated by the lights. He noticed that auroras seemed to coincide with disturbances in compass needles. The needles would wobble, point in wrong directions. This suggested some kind of magnetic connection, though he couldn't explain it fully. English astronomer Edmund Halley, also of comet fame, proposed that Earth's magnetic field was involved. In 1716, he suggested that the aurora might be related to Earth's magnetism, and that luminous material from Earth somehow reached the upper atmosphere. He was partially correct. Earth's magnetism is indeed crucial, though the luminous material comes from the Sun, not Earth. The connection between solar activity and auroras became clearer in the 1800s. As telescopes improved, scientists could study the Sun in more detail. They noticed sunspots, solar flares, patterns, and they noticed that auroras seemed more frequent during times of high sunspot activity. Correlation became apparent, but the mechanism remained mysterious. In 1859, a massive solar flare created the most powerful geomagnetic storm in recorded history, now called the Carrington event, after astronomer Richard Carrington, who observed the flare. Telegraph systems around the world went haywire. Operators received electric shocks. Papers caught fire from electrical surges. And the northern lights. They were visible almost everywhere on Earth. People in tropical Cuba, Colombia, Hawaii, all saw auroras. The Carrington event auroras were so bright, you could read a newspaper by their light at midnight. In the Rocky Mountains, miners woke up thinking it was dawn. They began preparing breakfast, only to realize it was still the middle of the night. The sky glowed red, green, white, pulsing with energy. If you're still listening, imagine a world lit by celestial fire. No electricity needed. Christian Birkeland, a Norwegian scientist, made crucial advances around 1900. He theorized that electrons from the Sun were guided by Earth's magnetic field to the poles. To test this, he created a miniature Earth in his laboratory, a magnetized sphere. He bombarded it with electrons in a vacuum chamber, and he successfully produced artificial auroras, glowing rings at the sphere's poles. Birkeland's work was initially controversial. Many scientists doubted that particles could travel from the Sun to Earth. The distances seemed too vast. But Birkeland persisted. He conducted expeditions to the Arctic, setting up observation stations, gathering data. His dedication was remarkable, working in brutal cold, enduring hardships, all to understand the lights. Let your breathing slow. We're halfway through our journey. In the 1930s, scientist Sidney Chapman developed detailed theories of geomagnetic storms. He explained how solar particles could disturb Earth's magnetic field, creating cascading effects. His mathematical models described the phenomenon with precision. Chapman's work laid the foundation for modern magnetospheric physics. The space age revolutionized aurora science. Satellites launched in the 1960s and 70s could observe the Sun directly, monitor solar wind, track particles traveling through space. For the first time, scientists could see the entire process, from solar flare to interplanetary travel to atmospheric collision. The pieces of the puzzle came together. In 1958, American scientist James Van Allen discovered radiation belts around Earth. These belts, now called the Van Allen belts, are regions where charged particles are trapped by Earth's magnetic field. They play a role in aurora formation, acting as reservoirs of particles that can be released during geomagnetic storms. We now know that magnetic reconnection is a key process in aurora generation. Magnetic reconnection is when magnetic field lines break and reconnect in new configurations. This releases enormous amounts of energy when Earth's magnetic field interacts with the solar wind. Reconnection can occur. This accelerates particles toward the poles. Those particles then create auroras. Modern spacecraft continuously monitor space weather. Satellites like SOHO and ACE provide real-time data on solar activity and solar wind conditions. This information helps predict auroras, and more importantly, helps protect satellites and power grids from dangerous geomagnetic storms. Understanding the northern lights has practical value beyond mere curiosity. Let's return to the colors of the aurora. Each one has its own story, its own beauty. Green auroras, as we mentioned, come from oxygen at lower altitudes, around 60 to 150 miles up. But there's more to say about this remarkable green. The specific shade of green can vary. Sometimes it's pale, almost white green, like moonlight through spring leaves. Other times it's vivid, bright lime, neon, intense enough to cast shadows on the snow below. The intensity depends on how many particles are hitting the atmosphere, how energetic they are. Green auroras often form curtains or bands. Imagine translucent drapes hanging from the heavens, swaying, rippling gently in an unfelt wind. These curtains can stretch across the entire sky, hundreds of miles long, but often only a few hundred yards thick, ethereal, delicate, yet powerful. Red auroras require high-energy collisions. The oxygen atoms need to be struck hard enough to emit red light instead of green. This typically happens at very high altitudes, above 150 miles, where the atmosphere is incredibly thin, or during extreme geomagnetic storms, when particle energy is exceptionally high. Red auroras can appear as a soft glow at the top of green curtains, like a crown, a halo of crimson, or sometimes the entire sky takes on a red tint, especially during major storms. Ancient observers who saw these all-red displays sometimes thought the sky was bleeding or on fire. But it's just oxygen, glowing at a different wavelength, peaceful despite its dramatic appearance. If you're still awake, picture a sky washed in gentle red, like dawn, but at midnight. Purple auroras blend nitrogen blue with oxygen red. The combination creates that royal purple, that majestic violet. These often appear at the lower edges of displays, where different atmospheric layers interact. Purple auroras have a regal quality, noble, rich. Pink is another aurora color, though less common. It's a mix of red and blue light, often appearing in the same way purple does. But pink auroras tend to be more delicate, softer, like watercolor washes across dark paper. Blue auroras are the rarest in nature. That electric blue, vivid, almost artificial looking in its intensity. They appear at the absolute lowest altitudes where auroras can form, where nitrogen is most dense. Some aurora photographers spend years trying to capture a truly blue aurora, They're that uncommon. White auroras are usually mixed colors. When all the colors blend together, or when a display is particularly bright and saturated, it can appear white or cream-colored. These are often the fastest moving auroras, pulsating, flickering. Like cosmic lightning, the human eye doesn't see aurora colors as vividly as cameras do. Our eyes have two types of photoreceptors: rods for low light, cones for color. In darkness, our rods dominate, but they're not good at detecting color. So when you see auroras with your own eyes, they often appear as greenish-white or grayish-green movements. The colors are there. Your brain just interprets them subtly. Auroras don't just vary in color. They also form different patterns, different structures. Each type has been classified, named, studied. Arc auroras are the most stable form. They appear as smooth arcs stretching across the sky, like ribbons or highways of light. These arcs can remain relatively still for minutes or even hours, gently glowing, marking the edge of the auroral oval. Band auroras are arcs with visible structure. Instead of smooth, they have folds, waves, like a curtain caught in a slow breeze. The lower edge is often sharply defined. The upper edge fades gradually into darkness. Curtain auroras are more dynamic. They ripple, undulate, move like fabric in wind. Sometimes they fold in on themselves, creating three-dimensional effects, depth and shadow. Though there's nothing solid there, curtain auroras are mesmerizing to watch, always changing, never still. Corona auroras appear directly overhead. When you're standing beneath the aurora's center, the converging perspective creates a corona effect. Lines of light radiate from a central point, like looking up into a cosmic flower or a starburst. It's a special viewing position, right under the action, immersive, overwhelming in the best way. Breathe deeply. Let these images fill your mind. Pulsating auroras flicker on and off, like a slow strobe light, brightening, dimming, brightening again. The pulsations can be regular or irregular, sometimes covering large areas, sometimes small patches. Scientists believe these pulsations are related to waves in Earth's magnetic field, cycles of particle acceleration and deceleration. Diffuse auroras glow softly without much structure. They're like a faint luminous fog, a gentle background glow across part of the sky. Less dramatic than curtains or bands, but peaceful, meditative. Auroral rays are vertical striations, thin lines of light, running from horizon upward, sometimes parallel, sometimes converging. They're following Earth's magnetic field lines, made visible by glowing gas. Rays can appear suddenly, shoot upward, then fade, like searchlights from the Earth. Auroras can move at different speeds. Some drift slowly, taking minutes to cross the sky, stately, unhurried. Others flash and dart, appearing and disappearing in seconds. Energetic, almost playful. The speed depends on how turbulent the magnetosphere is, how quickly particles are being injected into the atmosphere. Auroral substorms are periods of intense activity. During a substorm, the aurora suddenly brightens, becomes more active, spreads over a larger area. This can last from a few minutes to a few hours. Then activity decreases again. Substorms are triggered by sudden releases of energy stored in Earth's magnetic tail, a region of the magnetosphere on the night side of Earth. Imagine the light suddenly exploding into motion, filling the sky, a symphony reaching crescendo. Earth isn't the only planet with auroras. Other worlds in our solar system also display these light shows, each unique. each shaped by that planet's characteristics. Jupiter has the most powerful auroras in the solar system. Jupiter's enormous magnetic field, its rapid rotation, and its volcanic moon Io, which constantly spews charged particles, all contribute. Jovian auroras are hundreds of times more energetic than Earth's. They glow in ultraviolet light, visible to spacecraft with the right instruments. Saturn also has impressive auroras, like Jupiter. Saturn's auroras are driven by both solar wind and internal sources. Particles from Saturn's rings and moons contribute. Spacecraft have captured images of glowing ovals at Saturn's poles, blue, violet, shimmering in the darkness of space. Mars has a strange type of aurora. Mars lost its global magnetic field billions of years ago, so it can't funnel particles to its poles like Earth does. But Mars does have localized magnetic fields, patches of magnetized crust in certain regions. When solar particles interact with these patches, discrete auroras form, not at the poles, but wherever the magnetic fields happen to be. Martian auroras are diffuse and would be invisible to human eyes, but they're there. Uranus and Neptune likely have auroras too. Though less has been observed directly, these ice giants are so far from the Sun, from Earth, from our spacecraft, but they have magnetic fields. They receive solar wind. The conditions exist. In the darkness beyond Saturn, these distant worlds probably glow with their own cold lights. If you're still listening, imagine that. Auroras on worlds no human has ever visited, dancing unseen. The northern lights aren't just beautiful, they can affect our modern technology. The same geomagnetic storms that create spectacular displays can also cause problems. Strong auroral events can disrupt radio communications. The charged particles in the ionosphere change its properties. Radio waves that normally reflect off the ionosphere can be absorbed instead. This affects aviation, ships, military communications, ham radio operators. During major storms, certain radio frequencies become unusable. Auroral activity can damage satellites. Satellites in low Earth orbit pass through the auroral regions, through zones of intense radiation. During geomagnetic storms, the increased particle flux can cause problems. Computer errors, sensor malfunctions, even physical damage to solar panels and electronics. Satellite operators monitor space weather carefully. Sometimes they put satellites into safe mode during storms, protecting them until conditions improve. The northern lights can induce electrical currents in power grids. When the magnetic field fluctuates rapidly during auroral storms, it creates changing magnetic fields at ground level. These changing fields can induce electric currents in long conductors, like power lines, pipelines, railway tracks. These are called geomagnetically induced currents, or GICS. In 1989, a geomagnetic storm caused a massive power blackout in Quebec. The entire province of Quebec, 6 million people, lost power for 9 hours. The storm induced currents that overloaded transformers. Protective systems triggered. The grid collapsed. It happened in March, still cold. Homes without heat, hospitals on backup generators, all because of particles from the sun, creating auroras and disrupting human infrastructure. Modern power grid operators now have space weather protocols. They monitor forecasts. During predicted storms, they can adjust grid operations, reduce loads, protect transformers. The beauty above requires vigilance below. It's a reminder that we live in a connected system. Earth, sun, space, all affecting each other. GPS systems can be affected by auroral activity. GPS relies on precise timing of signals from satellites. Those signals pass through the ionosphere. During geomagnetic storms, the ionosphere becomes turbulent. Signals can be delayed, scattered, degraded. This affects navigation accuracy, usually by just a few meters, but for precision applications, aviation, surveying, it matters. Airlines adjust flight routes during major auroral storms. Polar routes, flights over the Arctic between North America and Asia, are efficient, but they expose aircraft to more radiation during solar storms, and communication with those aircraft becomes more difficult when radio is disrupted. So during major events, airlines reroute, flying at lower latitudes, staying away from the auroral zones. Safety always comes first. Let your mind drift with these facts, like clouds across a peaceful sky. Scientists use auroras to study Earth's magnetosphere. The lights are visible evidence of invisible processes. They reveal what's happening in space around our planet. By watching where auroras form, how they move, what colors they display, scientists can infer properties of the magnetosphere. It's like reading a message written in light. Networks of cameras now monitor auroras continuously. Across Alaska, Canada, Scandinavia, Iceland, automated cameras point skyward every night. They capture images every few seconds, creating time-lapse records of auroral activity. This data helps researchers understand auroral dynamics, predict space weather, and create stunning videos for the public to enjoy. Beauty and science working together. Many people describe seeing the northern lights as a spiritual experience. There's something profound about standing beneath them. The scale, the beauty, the silence. You feel small, connected, part of something vast. Even knowing the science, the physics, doesn't diminish the wonder. If anything, it enhances it. The aurora is often silent, but the experience isn't. You hear the crunch of snow under your boots, your own breathing in the cold air, maybe the wind, the distant sound of a river, and above, the silent dance of light. That contrast between the stillness of the lights and your own physical presence, it creates a meditative state. Many people report that aurora viewing is one of the most peaceful experiences of their lives. Aurora tourism has grown significantly in recent decades. Entire industries have developed around showing people the lights. Hotels, tours, photography workshops. Communities in the Arctic welcome visitors, share their knowledge, their culture, their skies. It's become a bucket list experience, something people save for, travel thousands of miles to witness. The best aurora experiences often involve patience. The lights don't perform on command. You might wait hours or see nothing at all on a given night. But those who wait, who bundle up and stay out in the cold, who keep watching, they're often rewarded, and the reward is sweeter for the patience required. Some people have devoted their lives to photographing auroras. They spend weeks at a time in the Arctic, enduring extreme cold, isolation, discomfort, all to capture that perfect shot, that moment when the lights explode in unexpected patterns, unexpected colors. Their images inspire millions, bringing the aurora to people who may never see it in person. Art, in service of nature's art. If you're still awake, imagine yourself there. Cold air, dark sky, and above, the dance begins. The aurora connects us to our ancestors for thousands of years. Humans have looked at these lights, wondered, created stories. We stand in an unbroken chain, looking at the same phenomenon they saw, feeling perhaps similar awe. Technology changes, understanding changes, but the fundamental experience remains. Every aurora is unique. No two displays are ever exactly the same. The colors, the patterns, the movements, the intensity, each one is a singular event, happening once, then gone forever. This impermanence adds to the beauty. You can't save it, possess it, only experience it, then let it go. The northern lights remind us of our place in the cosmos. We live on a small planet, orbiting an ordinary star, protected by a magnetic field. That field channels particles. Those particles create light, and we, conscious beings, get to witness it. It's a chain of physics, chemistry, biology, all coming together in a moment of beauty. Scientists continue to make new discoveries about auroras. Despite decades of study, mysteries remain. Subtle processes, unexpected behaviors, new satellites, new instruments, new analytical techniques, they all reveal new details. The aurora, still teaching us, still surprising us. Our understanding grows, but so does our appreciation for how complex, how beautiful nature truly is. The northern lights will continue long after we're gone. As long as the sun shines, as long as Earth has its magnetic field, the auroras will dance. They danced before humans existed. They'll dance after we're gone. They're not for us, but we're privileged to witness them. A gift from the universe to anyone who looks up. And there you have it. 100 facts about the northern lights, about the aurora borealis, from ancient myths to modern science, from the physics of particles to the poetry of light. I hope these stories have carried you gently towards sleep, that your mind is calm, your body relaxed. If you're still awake, that's perfectly fine. Sometimes the mind needs time, and that's okay. Picture yourself one more time, standing in the Arctic night, snow beneath your feet, stars above, and there, on the horizon, a faint glow begins, green light, spreading, growing, rising into arcs, then curtains, dancing, swaying. You watch, breath forming clouds in the cold air, and you feel connected to Earth, to sky, to the cosmos itself. The lights move, shift, change colors, purple edges, red crowns, the whole sky alive with silent beauty. And you stand there, small but present, witnessing, grateful. Let that image stay with you as you drift, as you fall into sleep. The northern lights, eternal dance of particles and magnetic fields and glowing gases, continue their performance. And somewhere, right now, they're dancing over Norway, over Alaska, over the frozen Arctic Ocean, dancing for no one, dancing for everyone, dancing because the universe is beautiful. Let your breathing slow. Let your muscles release their tension. Let sleep come, gentle as auroral light. The cosmos is vast, but tonight, you've traveled through a small part of it. 100 facts, 100 moments of wonder. May your dreams be filled with dancing lights, with peaceful skies, with the quiet magic of the north. Thank you for listening, for staying with me through this journey. Rest well, sleep deep. Good night.